Hey everybody, we're going to get started with chapter 7 this week. We're working on chemical reactions. We're going to learn how to write a chemical reaction from a chemical equation, and we're also going to do the reverse. So take a chemical reaction that's written in words and write it as an equation. We're also going to learn how to balance equations. So those are the three major topics. Along the way, we're also going to learn about some of the different types of chemical reactions and how to classify those. Without further ado, let's get into it. Let's review chemical and physical changes. So we talked about this in chapter 3 when we were talking about states of matter and things of that nature. We also talked about chemical changes, physical changes, chemical and physical properties. Since we're going to be talking about chemical reactions, we need to talk about chemical and physical changes. Remember that a physical change means that the composition of the substance remains constant. So a physical change, we're talking about a change of state or shape. So liquid water is being frozen to ice, or maybe you're taking a piece of metal and cutting it, things like that. With a chemical change, you're doing a chemical reaction. So the composition of the substance is going to change. During a reaction, you're going to make a new substance. So that's the difference between physical change and a chemical change. This should be a little bit of a review. If it's not, let me know. Now, there's some evidence that we can use to detect when a chemical reaction is occurring, because you can't see what's going on, with all the individual atoms. My eyes can't do that. Maybe yours can because you got young eyes, but mine cannot. So there are 4 observations that you can make, and each one of them is an indication of a chemical reaction. So you don't need to see all 4. You just need to see at least one of these for evidence that you're looking at a chemical reaction taking place. The first one is that a gas is produced. So you might see a lot of fizzing and bubbling, or you might just see a little bit of fizzing and bubbling. It doesn't have to be super crazy heavy. But if you think about adding an antacid to water, it's going to fizz and bubble, and that means that a gas is being produced and released. So here, if you put magnesium metal in an acid, you're going to form hydrogen gas. And that hydrogen gas is going to be causing all the bubbling that you see in this flask. Another piece of evidence you can use to know that a chemical reaction is occurring is that you produce an insoluble solid. So you mix 2 substances that are aqueous solutions, which just means that you have 2 substances that are both dissolved in water. You mix them together, and then all of a sudden you see a solid form. So this yellow stuff here, that's called a precipitate. It's an insoluble solid. You will need to know that word, along with aqueous solution. So underline those. Make sure you know these words. The third piece of evidence you can look for is a permanent color change. Lots of reactions involve a color change. So it may go from clear to a color, from a color to clear. A color change means that you've made a new substance. The last piece of evidence you can look for is a change in energy. Some reactions will release heat. That's called an exothermic reaction. So if you mix 2 things together and the flask gets warm, that's exothermic. Some reactions will absorb heat. That's called an endothermic reaction. It requires energy to take place. So it's going to take that energy from its surroundings. So you might notice the flask gets cold when you mix them together. You will also need to know these terms, exothermic and endothermic. So let's do a little bit of practice. I would suggest that you pause it and take note of which one of these, is it a chemical reaction or is it not? So I put chemical reaction or null, okay? So pause it, label whichever ones is chemical reactions and the other ones is not. And I'll go through it. Number 1 says mixing baking soda and vinegar results in the formation of bubbles. We're definitely going to call that a chemical reaction. Formation of bubbles means that you're making gas. So that's your clue there. Number 2, cooling carbon dioxide results in the formation of dry ice. We don't see any kind of bubbles being formed. There's no precipitate, no color change, and there's really no energy changes. So this is a physical change. So we're going to say, nah, that's not a chemical reaction. Just cooling something down is a change of state. Number 3, 2 liquids are combined in a green precipitate forms. Well, we've got a permanent color change and a precipitate. So that's absolutely a chemical reaction. So you'll need to be able to tell the difference. This is just a little bit of practice to give you an idea of what these things might look like on a quiz or an exam. Now we're going to move on to writing chemical equations in words. I'm first going to go through this equation slowly and kind of point things out to you. And then I'll show you a chart that has a lot of the symbols that are used in chemical equations that you may want to have in your notebook when you're doing this for your homework. The first thing you'll notice is that you've got 2 sides that are separated by this arrow. The left-hand side is the reactants. These are the ingredients, right? So if you're baking or you're cooking something, you've got your ingredients that you're going to put together to make something new. That's what the reactants are. On the right-hand side of the arrow, you've got your products. That's what you end up with. So if you're making brownies, you're going to have the flour and the cocoa powder and all that stuff. Those are your reactants, your ingredients. You mix them all up, you put it into a pan, put it in the oven. When you pull it out, your product is the brownie. This arrow, you can think of it as being the word yields, okay? So if you put these things together, they will yield these different products on the right-hand side. You'll notice that after each compound, there's some little abbreviation in parentheses. Now, we encountered the AQ in chapter 6 when we were talking about acids. So that should be review. AQ in parentheses is aqueous. The only difference here is that for chapter 7, it doesn't have to just mean an acid. It just means something dissolved in water. The S in parentheses means that whatever compound is a solid. The L is liquid, and the G is gas. So you always want to indicate the state of matter. For every compound in a chemical equation, whether you're writing the chemical equation as it is here, or you're writing it in words, you need to indicate the state of matter. The other thing you're going to need to be able to do is name compounds. So chapter 6, that's all we did was naming ionic compounds, molecular compounds, and acids, the aqueous acids. You will need to know how to do that in order to do chapter 7. So if you're like, oh, wait, hold up, so I got to name stuff, then you need to go back to chapter 6. I told you everything builds. So if you don't get the major concepts from the chapter previous, the next chapter, it won't work. So let's write this bad boy in words. We've got to name everything first. So I'm going to write down the compounds that we have. So these are our reactants. And then our products. Let's start with our reactants. That makes the most sense, right? The first one, you have to know that this, and I'll add in some chapter 6 review, this is a ternary oxyacid because it's made of an oxyanion plus a hydrogen. The name of this ion is acetate, so it is acetic acid. The 8 goes to ic, remember that. This next one, we didn't talk about bicarbonate, but if you take carbonate, which is CO3 2-, that's the ion, and you add a hydrogen, it becomes bicarbonate. So I wouldn't require you to know this because we didn't talk about it. That's why I'm giving it to you as an example. We still treat that bicarb like it is, like it's an ion, because that's what it is. It still has a charge. So that's a ternary ionic compound. So those are our reactants. Now let's move on to the products. We've got sodium acetate, and that's a ternary ionic compound. H2O, that's a binary molecular compound. You could name it dihydrogen monoxide, but you can also just call it water here. CO2, that is another binary molecular compound. You name the first element, which is carbon. Then you indicate how many you have of the second element using the prefixes. Then you name the element using the kind of the same thing as we use for the monoatomic anions, where it's the first syllable followed by IDE. So we went through and named everything. Let's make sure that we add in the state of matter. So for our reactants, we've got aqueous acetic acid. That's sodium bicarb. Oops, see, I'm writing sodium. The sodium bicarb is a solid. Sodium acetate, aqueous. Water is a liquid. Carbon dioxide is a gas. Now we have to write this as a sentence. We're going to talk about the reactants first, and then we're going to say something like are combined or yields, something like that, and then talk about the products. I'm going to get colorful on y'all. I'm going to write about the reactants in blue. Aqueous acetic acid and solid. Writing solid and sodium right after each other, my brain just can't handle it, y'all. Solid, sodium, bicarbonate. That's our reactants part. Now we've got to talk about the arrow. So I'll do this part in red. And I just noticed, hold on. I'm going to get it together one of these days. You can have an off day too. It's all right. Now we'll talk about the arrow. So it's yields or something like that. For this, we're combining two things. So I can say aqueous acetic acid and solid sodium bicarbonate are combined to yield. And that's a pretty safe phrase that you can use just in general. The only time that you wouldn't want to do that is if you've only got one reactant. You're not combining it with anything. Now we're going to do the products. So those two things are combined to yield aqueous sodium acetate liquid water and carbon dioxide gas. So that is how you would write that in words. Now there's a little bit of leeway here. You know, everyone has their own style, but you always want to make sure that you have the reactants first and you talk about their states of matter, that they're combined to yield, mixed to yield, or if you've only got one thing and it is making multiple things, that means it's decomposing, which we'll talk about that in a second. So you can say decomposes to yield, but you're going to say something about yields. Then you talk about what products you make. So in this case, we have the aqueous sodium acetate, liquid water, and carbon dioxide gas. Now, this reaction is something that you may have done before because it's just mixing vinegar, which is acetic acid, and baking soda to make a baking soda volcano. The only thing that you don't see here is to make the bubbling a little bit more dramatic, you add some dish detergent. So Palmolive or some Dawn or something. Not a sponsor. And that will make the bubbling, you know, a little bit more dramatic and fun. You can add some food coloring, but that's all this is. Baking soda volcano. You're welcome. Now you can describe it to someone and use all those highfalutin words, and they're going to be like, wow, you're really smart. You're going to be like, yeah, I am. You're welcome. So, as I promised, here's a chart that has all the chemical equation symbols that you might encounter. So we covered the yields. I didn't talk about the plus sign. That's kind of intuitive, but it just separates the reactants and the products. If you've got multiple reactants, multiple products, you're going to separate them with the plus sign. If you have a little triangle over your yield sign, that means that you're using heat. If you see an element over the yield sign like iron or platinum, that means that it's a catalyst. So it's not a reactant or a product. It's just something that helps to accelerate the reaction. NR stands for no reaction. And then we've got all of the states of matter, the S, L, G, and AQ for solid or precipitate, same thing. Liquid substance, gaseous substance, and aqueous solution. So all of these are things that you may encounter when you're looking at a chemical equation. Let's do another one. This time, we've only got one reactant. And then we're making multiple products. So let's do our naming first. So we've got that as our reactant. Let's classify it too, just for some more practice, because you'll need to know it for the exam as well. So your next exam 4, as well as the final exam. So take all the practice you can get. Classify and name everything you see. So this is a ternary ionic compound. You've got the metal plus the polyatomic anion. The metal is aluminum. It's not a transition metal, so you just write aluminum. Then you name the ion, the negative ion. So that's our reactant. We've got two products here. We already know what CO2 is because we just did that one. That's carbon dioxide. And it's something that you probably recognize anyway. But it's a binary molecular compound. Now we've got Al2O3. That's a binary ionic compound. Again, we're just going to name the cation, which is aluminum. And then we're going to name the anion. It comes from oxygen. So you use ox and then add IDE. Again, if this is troubling you, if you can't do this as fluid, then you need to continue to practice your naming. Because naming needs to come pretty easily by the time you get to exam 4. Otherwise, it's going to take you a really long time to do the exam. So there's all of our naming. Try to keep consistent here. We'll talk about the reactants in blue. And we also need to make sure that we indicate our states of matter. So I like to start off with the state of matter followed by the name of the compound. So solid aluminum carbonate. That's the reactants. Now we've got to do this part, the yields. And it's got a little triangle over it. So remember that chart I showed you? You're going to need it. So that triangle over the yield sign means that you're adding heat. So we can say is heated to yield. But you're going to want to include that heat, okay? Because that is part of the reaction. You're pretty much giving the recipe for how to make these products. So if I tell you in a baking recipe that you need to use butter, you need to know if you need it to be melted butter, room temperature softened butter, cold or frozen butter that you grate. You need to know the details on that, okay? So that's why you have to tell the reader every single detail about the chemical reaction in words. So far we have solid aluminum carbonate is heated to yield. Now we talk about our products. We've got solid aluminum oxide. And carbon dioxide gas. You may also see gaseous carbon dioxide. Same thing, just giving you two different ways to write it. So that's writing a chemical equation in words, and I'll give you plenty of practice for that. Any equation that you see from now going forward, you can name all the compounds, classify all the compounds, and at least in your head, think about how you would write the equation in words. Now let's do the reverse. we have the written text for a chemical equation, and we need to write it as an equation. That chart is going to come in handy again to make sure that you're using all the symbols properly. I'm going to go through and circle everything that is a reactant. So we have solid magnesium metal and oxygen gas are combined. Okay. We've hit that are combined, so that means that everything before it, we're talking about reactants. Are combined, that's our yield sign. Ooh, and heated to yield. So that's all the arrow, okay? Then we've got solid magnesium oxide. That's our product. So just like in chapter 6, where you need to be able to go from the name to a chemical formula, you're going to need to do that when you're taking a written description of a chemical equation and writing the chemical equation. So the first thing you want to do is start with the reactants. We've got solid magnesium metal and oxygen gas. Magnesium metal is simply Mg, and then you put the S after it in parentheses for solid. So anything that you see that's a metal, sodium metal, calcium metal, anything metal, and it's solid, you're going to put just simply that element symbol followed by the S in parentheses, or whatever state of matter it's in. It could be a liquid. Then we're going to put a plus sign because we have to write another reactant. And we've got oxygen gas. Oxygen gas always comes as a diatomic molecule. And I'm going to talk about that in just a second. But just take my word for it for now. That oxygen gas is O2. Now we've reached the are combined and heated to yield. So we know that's the arrow, and it's heated, so we've got to have that triangle. Now we're at our products. Solid magnesium oxide. Remember that you want to make sure that you're writing all of your chemical formulas properly. Magnesium, its ion is 2+ because it's from the group 2A and it's a metal. So its charge is 2+. Oxide, the oxide ion, is 2-. Oxygen, when it forms an ion, the charge is -2 because you can take that, the group number 6 minus 8, and that gives you your charge. So again, if chapter 6 is a struggle for you, then this part of chapter 7 is also going to hurt. Make sure that you can write chemical formulas very easily. So this is our final answer, what I boxed. Magnesium solid plus oxygen gas combined and heated to yield solid magnesium oxide. Let's do one more, but I'll encourage you to pause it, try it on your own first, and then you can look at the answer. I would also recommend that if you can, when you're doing these on paper, kind of separate and label the reactants, the yield, and the products, and that will make it easier for you to kind of follow along and make sure that you've got each piece in your equation. Cadmium metal is added to aqueous cobalt 2 nitrate to produce aqueous cadmium nitrate and cobalt metal. Cadmium metal is added to aqueous cobalt 2 nitrate. Those are the reactants. to produce, that's our arrow. That's our yields. Then we've got the list of the products: aqueous, cadmium nitrate, and cobalt metal. Let's start with the reactants. Cadmium metal, that's a solid. So anytime you see something like cadmium metal, when you see the word metal and it doesn't have a specific descriptor of the state of matter, assume it's a solid. Is added to aqueous cobalt 2 nitrate. So cobalt 2 is 2 plus. Nitrate is NO3 minus. So you're still going to need that chart, the polyatomic ions chart. In order for us to write a balanced chemical formula, we're going to need to have 2 of these nitrates here. And we're told that that is aqueous. So we're combining those to produce, that's our arrow, aqueous cadmium nitrate and cobalt metal. So cadmium is a transition metal, but it is one of the exceptions. It only forms one ion. So cadmium forms a 2 plus ion. So just like the cobalt, we're going to need to have 2 of these nitrates so that our formula is overall neutral. And then the cobalt metal is a solid. There you have it. Writing a chemical equation from a written description. We'll do more practice of this, and I'm going to keep saying it. I'm sorry. Broken record. Forgive me. If you can't do chapter 6 with naming and writing chemical formulas, then you will not be able to do chapter 7. So make sure that chapter 6 is smooth and solid for you, because otherwise you will not do chapter 7 very well at all. The next part we're going to get to is classifying chemical reactions. So we're able to write them now. Now we need to classify them. There's 5 types of reactions that we're going to talk about today. Combination reactions, decomposition reactions, we'll start with those 2. Then we'll move on to single replacement, double replacement, and neutralization. Combination reactions. Pretty much what you're doing is taking simple substances and combining them into one more complex substance. You'll also see them called synthesis reactions. Same thing. An example, you're taking A, B, and C, and you're creating F, right? So you've got multiple reactants. And one product. That's the hallmark that you're going to look for. I'll give you some examples of combination reactions. When you mix a metal with oxygen gas and you heat it, you form a metal oxide. I'm just labeling it here. So we actually had this reaction that we had to write in words. So that's one example of a combination reaction. Again, notice that it's heated, so you have that triangle. Another example of a combination reaction would be oxygen plus a nonmetal reacting to make a nonmetal oxide. So if you take sulfur and combine it with oxygen and heat it, then you can make sulfur dioxide gas. Again, you don't need to know these exact reactions. Just understand that I'm giving you examples of combination reactions. And again, you've got multiple products forming multiple reactants forming one product. The third type of combination reaction you might see is reacting a metal and a nonmetal, and you're going to form an ionic compound. So those ternary ionic compounds, binary ionic compounds. So an example would be taking lithium solid metal. You heat that in the presence of bromine gas, and you produce lithium bromide. Multiple reactants, one product. The next type of reaction we're going to cover is decomposition reactions. So you're taking one complex compound and breaking it down into simpler substances. Oftentimes you're going to see heat. Most of the time you need heat for these decomposition reactions. It's pretty much the opposite of a combination. So you've got one reactant and multiple products. Here's some examples. You can heat mercury 2 oxide to produce liquid mercury metal and oxygen gas. You can also take calcium carbonate and heat it to make calcium oxide and carbon dioxide gas. So those are just examples, but you see one reactant, two products, and it's heated. The heat doesn't have to be there. It will oftentimes be there. But the real key is knowing that you're going from one reactant to multiple products. Before we move on to the next couple of reactions, we have to talk about the activity series concept. The activity series is talking about metals and how reactive they are. Metals can replace each other in reactions, but only if one metal is more active than the other. And the activity of a metal is just its ability to compete in a replacement reaction. This is the relative activity series right here. So lithium is the most reactive, and it will replace everything else. Gold is the least reactive. It ain't replacing nothing, okay? Everything in between is relative. So if I looked at SR, which is strontium, that is going to be less active than barium, more active than calcium. It's also going to be more active than cadmium and silver. So think about this, it's 3 lines, but think about it as one continuous line. Just can't fit it all like that on a slide. So I want you to pause for a second and choose the most active metal in each pair, just to make sure that you get it. It's a very simple concept. You want to make sure that you get it because you need it for the next couple of reaction types. Now, let's look at zinc and mercury. I'm going to use a different color for each of these. So for the first one, I'll do red. We've got zinc. We've got mercury. The most active metal is going to be the one that comes first. Zinc comes first, so it is more active than mercury. We'll do green for the next one. We've got copper, which is here, and tin, which is SN, here. Which one comes first? Tin comes first, so it is more active than copper. Now we'll do lithium and iron. Lithium is first, and I already said it's the most reactive. So if you see lithium as a choice, and the question is which is the most active metal, there's your answer, lithium. But just to show, we've got two things in two different rows. Lithium is still the answer. Lithium comes before iron, so it is more active. I will provide you with the activity series. You do not need to memorize it. Now that we've got the activity series concept down, we can talk about replacement reactions. The first one we'll cover is single replacement. That's simply where a more active metal displaces a less active metal in a compound. So here we've got solid iron, and we're adding it to an aqueous solution of copper 2 sulfate, which is a very pretty blue color. Sometimes chemistry is just pretty. You gotta just look at it in awe. When you add in iron, which is this rod here, iron is more active than copper. So it's going to replace the copper, and you're instead going to have iron 2 sulfate and copper solid. So you'll start to see like copper flakes over time accumulate in the bottom of the beaker. Let's do one. Will solid silver react with aqueous copper 2 nitrate? Let's first write that out so that we kind of see what we've got. Solid silver, we can write it like that. And we're adding that to aqueous copper 2 nitrate. Copper is Cu, and copper 2 has a 2+ charge. Nitrate, that's NO3-. So we're going to need 2 of those. So we need to use the activity series to see if that silver is more or less active than copper. Here's copper, here's silver. Copper is before silver, so that means that copper is more active. So we're not going to have a reaction here. That silver is just going to hang out and sit. So will it react? No. There's no reaction. We'll do more practice like this in class, but that's the type of question you'll need to be able to answer with the activity series to determine whether or not something is a single replacement. So here's some more practice that you can do. You can pause it, try it, and then check your work. In the first question, we've got zinc and lead. We've got zinc and lead for both of these. So let's just look at where zinc is. Here's zinc. Here's lead. Zinc comes before lead, so zinc is more active than lead. So in the first one, where we're adding zinc solid to lead 2 nitrate, we're absolutely going to have a reaction. And we're going to make some lead solid and zinc nitrate. For the second one, we're adding lead to the zinc nitrate. Since zinc is more active, there's going to be no reaction. I'm not going to require you to be able to write out the products like this per se, but you do need to know whether or not a replacement reaction is going to occur. I may also require you to be able to choose what the products are. So you should at least know that you're going to form solid lead, because that's what a replacement reaction is. Now we're going to keep talking about displacements. We're going to talk about aqueous acid displacements. This is still under the same category of single replacements. Only instead of a metal, we're talking about hydrogen, the hydrogen in an acid. Hydrogen is actually included in that activity series. And the metals that come before hydrogen will displace hydrogen in an acid. The ones that come after hydrogen will not. So it's the same idea, just a slightly different concept. So we're adding a metal to an acid. And if it is more active, then you will get replacement. So you make some kind of an ionic compound and hydrogen gas. If you have a metal that's less active, you're just going to have no reaction. So it's the same idea, just instead of two metals, we're talking about a metal being added to acid. The last type of single replacement we're going to talk about is an active metal plus water. Some metals are active enough to directly interact with water. These metals are super duper active. So group 1, like sodium, and you can also have some group 2s like calcium. They will directly interact with water and replace the hydrogen. You don't need to know how to label, oh, this is an active metal plus water, or this is an aqueous acid displacement. Just know that it is a single replacement. And there are a few different flavors of single replacement. If you can have single replacement, you can also have double replacement. In a double replacement reaction, you're going to have two ionic compounds in an aqueous solution. You're going to mix them together, and they're going to switch anions and make an insoluble substance. That's the precipitate. It must form a precipitate in order for it to be a double replacement reaction. Otherwise, there's no reaction. So you'll notice that I've color-coded these so that you can track them a little bit better. We've got barium chloride and potassium chromate. We're mixing those together, and we're making barium chromate and potassium chloride. So notice the barium, instead of it being with the chloride, it's now with the chromate. And that is insoluble. So there's an S behind it. We're forming a solid. Now, how do you know whether or not you're going to form a solid or a precipitate? Good question. Solubility rules. So you'll need to know these. I will provide the solubility rules for you as well. So you'll get the ions sheet, and you'll get solubility rules for exam 4 and the final exam. The first half of this table talks about things that are soluble. By and large, if you've got anything from group 1, so the alkali metal ions, or ammonium, if it's got either of those, it's going to be soluble. Things that are paired with the acetate ion, the nitrate ion soluble. Halide ions, mostly soluble, but there are some exceptions. So if you see silver, mercury 1, or lead 2 plus, those things are typically insoluble, okay? The sulfate ion, most things are soluble, but there are exceptions. Strontium, barium, and lead 2. The bottom part of the table talks about things that are insoluble. So if you see a compound that has carbonate, chromate, phosphate, sulfide, or hydroxide, it will likely be insoluble. The only real exceptions are the things with the alkali metals. So if you see LiOH, that's soluble. It's an exception. Everything else that you see, not going to be soluble. So this is kind of like a logic type thing. You have to take your compound and then look at the rules and see where it falls and figure out whether or not it's going to be soluble or insoluble. You can simplify that whole chart into this one rule that will help, but it doesn't tell you the exceptions. So all group 1 metal ions and ammonium nitrate and acetate ions are soluble in water. Everything outside of that, you might want to think about it, whether it's soluble or not. It may form a precipitate. So it doesn't tell you the exceptions for, but you can at least figure out, okay, I think this is probably soluble, or I should suspect this of being insoluble. But it's not a substitute for the chart. For the chart, you just have to practice. So I'll give you plenty of practice to say, okay, is this compound soluble or insoluble? And help you reason through it. So here's an example. We're mixing aqueous sodium chloride with aqueous lithium nitrate. We're going to swap the anions. So notice how the chlorine or the chloride was with the sodium. Now it is with the lithium. And the nitrate was originally with the lithium. Now it is with the sodium. So we've swapped ions. Now the question is, are either of these two compounds on the product side insoluble? Both sodium and lithium are in group 1A. So those are the alkali metals. If you see compounds with those, they're going to be aqueous. So this is really no reaction. You just got the same ions floating around in water. So this is not a double replacement reaction. Because we're not forming a precipitate. So you don't want to call it a double replacement just because you can swap the ions. You have to swap the ions and a precipitate is formed. The last kind of reaction is a neutralization. And that's when you take an acid and a base, you mix them together, and you form a salt. So think of an ionic compound and water. So an acid, it always has the hydrogen first. A base has hydroxide. So this is the OH. And then you're going to see that you form water. So I have an example below. There's your acid. There's your base. You have your salt, which is the potassium sulfate, and water. You have to be careful here because it looks a little bit like a double replacement. But notice there's no solids forming. Let's do a little bit of practice. You will need that solubility rules chart. So if you need to, write this down in your notebook, pause it, and then go back to that solubility rules chart and try these first three. Then we have whether or not this bottom reaction is a double replacement or a neutralization reaction. So let's start with soluble or non. We've got mercury 2 chloride. The exception is for mercury 1, which looks like this. We've got mercury 2. So that should be soluble. Next, we've got silver bromide. Silver, so it's bromide is a halogen. So typically those are soluble, but silver is an exception. It's insoluble. Lead 2 iodide, same thing. It is a halogen. However, lead 2 is insoluble when paired with the halogen. So that's practice for how to use that chart. Now we have a reaction here where we're mixing an acid and a base. We're forming a solid precipitate. And water. I'm not going to give you anything this tough. You could really argue it either way because you're adding an acid and a base together and you're producing a salt and water. But that salt is not aqueous. You're making a solid. So you should really label it as a double replacement. This is just an example to show you that you need to pay attention to those states of matter. So let's do a quick recap for classifying chemical reactions. Combination reactions, you've got multiple reactants. Looking at combination and thinking of decomposition. So multiple reactants forming one product. Decomposition is the reverse. We've got one reactant and it's breaking down into multiple products. Usually requires heat, but not a necessity. For single and double replacement reactions, well, let's actually not pair these up. Let's start with the single replacement. Single replacement reactions, we're talking about the activity series. So if a metal is more active than the other, it will replace that metal in solution. And again, you'll be given that chart. For double replacement reactions, you're mixing aqueous solutions and forming a solid plus another aqueous solution. You have to form a solid in order to be a double replacement reaction. Otherwise, there's no reaction. Finally, with the neutralization reaction, you're taking an acid plus a base. You're making a salt that is aqueous. And you're making water. Remember that a base is going to have something OH. And it could be multiple OHs, but you're just going to want to see that hydroxide ion with the base. So that's the recap. I would encourage you to put this, make sure this kind of a summary is in your notebook so you can reference it while you're doing your homework for mastering chemistry. So as I promised earlier on, diatomic molecules, we were writing a reaction from words, and I wrote oxygen gas as O2. The reason is it's one of the elements that in nature it exists as a diatomic molecule, which means there's two of them together. You're not just going to see O. It's always going to be O2. So shown here are the ones that form diatomic molecules. So it's hydrogen, and then you've got these others here: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They form a 7 in the periodic table. So these are the only ones that form diatomic molecules naturally, and that's the only way you see them. This is a list of all those. So you're definitely going to want to keep this in mind when you're writing your chemical equations when you're writing out your chemical equations, period. And also when you get to balancing equations, which is what we're moving on to. Balancing equations. Please don't sigh heavily like that. I've heard you. I've got mom ears. It doesn't have to be that hard. Just hold somebody's hand and get through it. So I'm going to give you first some tips and kind of what to look for when you're balancing an equation. Then I'm going to go through and balance a couple of equations for you and point out kind of the method that I use. We will do practice in class together, but you're going to need to practice. Practice makes perfect. So when you're balancing an equation, you're going to make sure that the number of atoms of each element is the same on the reactant side and the product side. That's the goal. You can do that by placing a whole number coefficient in front of the substance. So that coefficient is a multiplier. So if you have 3 in front of H2O, that means that you've got 6 hydrogens and 3 oxygens. So this is kind of like what we were doing at the end of chapter 3, where we're writing the composition of a compound. And what do you know? I've got some practice for that to remind you, because chapter 3 was a minuto ago. So how many atoms of each element are present in the following compounds? So take a second and do the practice just to refresh yourself. If you're like, man, I got this, fine. If not, and you're like, oh shoot, I don't remember this at all, refresh yourself. So in this first compound, we've got 3 elements: hydrogen, carbon, and oxygen. Let's first focus on just the compound. So we've got 1 plus 3 to make 4 hydrogens. We've got 2 carbons and 2 oxygens. But we've also got this multiplier out front, this coefficient. So that means that you're going to multiply everything by 2. So instead of writing 4 hydrogens, you're going to write 8 hydrogens. Instead of 2 carbons, you've got 4. And instead of 2 oxygens, you've got 4. So that's what that multiplier does. In this second compound, we've only got hydrogen. but it's got a subscript. So that tells us that there are more than one hydrogen atom in this compound. So we've got 2 hydrogen atoms. When you're balancing an equation, don't change the subscript. And just like that, that's the next slide. Sometimes I'm really purposeful, and sometimes it's just coincidence or serendipity, but I'll claim it anyway as brightness on my part. So the coefficients, those are the multipliers. Make sure that before you start adding coefficients, that your chemical formulas are correct, particularly if you're taking a written description of a chemical reaction and you have to write that out and then balance it. Double check and make sure that you've written your chemical formulas properly before you start adding coefficients. Never, ever, ever change the subscripts. Do not change that 2. However, putting something out in front, perfectly legal. We're going to change the coefficients on the different compounds to balance the number of atoms on each side. But you never change the subscripts. If you change the subscript, you're changing the compound. That's not what we're doing. We're just changing how many of them we have. When you're balancing an equation, you're going to start with the most complex formula. So if I have that versus, say, this, the H2, this barium nitrate is more complex. It's got more moving parts than just the hydrogen gas. So I'm going to start balancing there. I'm also going to leave that NO3 together as a group and balance it versus splitting it apart and balancing the number of nitrogens and oxygens. You can do that if you see that ion on both sides of the equation. And again, we're going to do some practice, but I want to give you some of the rules and tips. Then we'll do some practice, and then you can kind of review these and look at these tips as you're balancing equations on your own. The coefficients in your equations have to be whole numbers. So if you look up and you see a fraction somewhere, don't freak out. Just multiply by the denominator. So you got to multiply this whole thing by 2. And that way you get rid of that fraction. So don't leave it like that. Once you balance the equation, make sure that you've got the same number of atoms on each side. So on the reactant side, we can total up our hydrogens and our oxygens and do the same thing on the product side. On the reactant side, we've got 2 times 2 for a total of 4 hydrogens. And then we've got 2 oxygen atoms. On the product side, we've got 2 times 2 for a total of 4 hydrogens, because remember, we've got this multiplier here. And then we've got 2 times the 1 to give us 2 oxygen atoms on the product side. Those are equal. The number of atoms of hydrogen and oxygen are the same on the reactant side and the product side. Make some kind of a little chart and double check your work after you balance. The last thing you want to do is make sure that you've got the smallest whole number ratios. So if you have 2, 2, and 4, you can reduce that down to 1, 1, and 2. So this would be the answer. And this other one, while it's balanced, it would be wrong. So make sure you do that check. With all those tips and things in mind, I'm going to show you how I balance an equation. Before I start putting numbers anywhere, I'm going to make a chart. I'm going to figure out how many of each atom I have on each side so I can figure out where I should start with balancing. I've only got 2 atoms, iron and chlorine. On the reactant side, which I just label them R and P. You can label them however you want, but just make sure that you know what your labeling system is. So for the reactants, I've got 1 iron atom and 2 chlorine atoms, because we're looking at that subscript tells us that I've got 2. For the product side, I've still got 1 atom for the iron, but now I got 3 atoms of chlorine. So I'm going to start here by trying to balance this chlorine. The way that you balance is by looking for the lowest common denominator. So what is the smallest number that both that 2 and 3 can be used to divide and get an even number? That number is going to be 6. So if you divide 6 by 2, you get 3 here. And if you divide 6 by 3, you get 2. Now I'm going to check again. See where we're at. I've still got 1 iron on my reactant side. Now I've got 3 times 2, which is equal to 6 chlorine atoms. On the product side, I've got 2 iron atoms because of that multiplier, and I've got 2 times 3 for chlorine atoms, which is 6. Well, now my chlorine is balanced, but my iron is still unbalanced. So I need to add something to the reactant side so that I have the same number of atoms. That lowest common denominator is going to be 2. Notice how I didn't do anything else to the product side. I'll do my final check. I've got 2 atoms of iron, and 3 times 2 equals 6 atoms of chlorine. We've got this 2 multiplier out here, so it's going to be 2 times 1 equals 2 atoms of iron, and 2 times 3 is 6 atoms of chlorine. Now we're balanced because we've got the same number of atoms on both sides. So I like to do a chart after each time I add a number to my original chemical equation. That way I can keep track of what's balanced and what's not. As you get more comfortable, you may not need to do a chart every time, but I definitely recommend doing your initial chart to see where you are and where you should start balancing, and your final check. That way you can look for whether or not everything is balanced, and then double check and make sure that all of your coefficients are the smallest whole number coefficients that you can make. And with 2, 3, and 2, that's as small as we can get them. Let's do one more example. This time we're going to include some polyatomic ions. Sulfate appears on both sides of the equation, so I can keep it together when I'm making my chart. The same thing goes for the nitrate. I can keep it together. So when I'm writing this, I'm going to keep those ions together. It will make life a lot easier. So let's start counting. For the aluminum, I've got this 2 here as a subscript for the aluminum. And that's the only place that I see aluminum, so there's going to be 2 of those. SO4, I see a subscript outside of that parentheses. So that means there are 3 sulfates. For the barium, there's only 1. However, we see a subscript after the parentheses from the nitrate, which indicates that there's 2 of them. Now we go over to our product side, and let me label reactants and products. You don't have to label if you don't want to. If you just know that, reactants are on the left-hand side, products are on the right, that's fine. But for clarity, I want to do that for you guys. So for products, we've only got 1 aluminum atom. So that's a problem already. For the nitrates, we've got 3 because of this subscript here outside of the parentheses. That's another problem. Clearly, we are not balanced. For barium, we've got 1. And for sulfate, we've got 1. So this is very not balanced, okay? We're losing atoms, we're gaining atoms. We got to do something about this. We're going to start with the more complex thing to balance. Our nitrates, we've got 2 on one side and 3 on the other. That's the most complicated thing that we've got. Our lowest common denominator for those 2 numbers is going to be 6. So you find the place where nitrates appear on the reactant side and the product side. The reactant side, we're looking at barium nitrate. We've got 2 nitrates over here. Lowest common denominator is 6. So if we take 6 and divide by 2, we get 3. We find where nitrates are on the product side. Take 6, which is our lowest common denominator, divided by 3. You get 2. Let's do another check. Because we've changed more than just how many nitrates there are. We've also changed some of the other atoms. So let's do our check. We haven't done anything to change the aluminum or the sulfates yet on the reactant side. We have, however, changed the barium. We've got 3 times the barium and 3 times 2 for the nitrates. On the product side, we've changed the aluminum because now we've got 2 times Al. So that's 2. And then we've got 2 times 3 for the nitrates. Oops. We've still only got 1 barium and 1 sulfate on the product side. So let's deal with that next. If we add a 3 in front of the barium sulfate, that's going to multiply both of those by 3. And everything should balance out. But just to make sure, you can do one final chart to make sure all your craziness adds up. And I know you might be like, but Dr. Hefner, it don't take all of that. It may not take all of that for everybody. But if it does, that's okay. Because if you do it this way, you'll always see what's balanced and what's not. So it may take you an extra couple of minutes, but those extra couple of minutes can be the difference between passing and failing. And in my book, it's worth it. So we'll start fresh. And remember, we're going to use all of these coefficients that we added in to do this tally. So for the reactant side, we've got 2 aluminums, 3 sulfates. We've got 3 times 1 for the barium, which gives us 3. And 3 times 2 for our nitrates, which gives us 6. On the product side, we've got 2 times 1 for our aluminum, which gives us 2. 2 times 3 for the nitrates. I keep writing the nitrates and the sulfates. There we go. The order ain't always the same, so you just gotta remember that. That's why paying attention makes this a lot easier. When you make a mistake, you'll catch it. So now we're looking at the nitrates, and that's 2 times 3 is equal to 6. Now we're looking at barium. 3 times 1 gives us 3. And the sulfates, 3 times 1 also gives us 3. Everything balances out, so we're good to go. You don't have to add a coefficient in front of every single compound. We didn't add anything in front of this aluminum sulfate. We just added coefficients for the other 3 compounds in the reaction. And that's perfectly fine. That brings us to the reminders. Don't worry, we'll do practice in class for balancing equations. You will absolutely need to know how to balance an equation to get through chapters 8 and 9. So you cannot slide by if you can't balance equations. Keep that in mind. You're probably not going to be watching this video before class. That's okay. You have an exam 3 this week, so you may have already taken it before you watch this video. That's totally fine. But I'm putting it out there because this is coming out before your exam. That exam will be available Wednesday, October 7th through Friday, October 9th at 11:59 p.m. Eastern Time. So make sure that you start the exam when it's still available. Don't email me at 11 o'clock on Friday night saying that you have an issue or that you can't find the exam. I'm not going to see that message. So you need to stay on top of stuff and know where to go. If you've got questions, you know you need to come to me beforehand. There's going to be a folder labeled Exam 3 in the course content. It's going to have your exam, periodic table, and it's also going to have the ions. Print out the periodic table and the ions to use on the exam. You're going to have Chapter 7 Mastering Chemistry homework and quiz due on October 11th. So that is the Sunday after your exam. Make sure you do that. I'm not giving you a chapter check-in, so make sure that you do that homework. If you don't understand Chapter 7, Chapter 8 and 9 are going to be really difficult. And finally, plug for office hours, Wednesdays 2 to 4. If you need something outside of that, you need to let me know. I try to only do individual meetings on Mondays and Wednesdays. So if you send me a course message on Wednesday asking when can we meet, unless it is an emergency, I'm going to tell you I'm not available until Monday. So keep that in mind. If you need help with your homework, don't ask me on Thursday if we can meet tomorrow, Friday, because the answer is going to be no. So make sure that you got your stuff together, and even if you can't start the homework, take a look at it. Make sure that it's like, okay, I think I can do this. And if you can't, you can always send me a message through course messages. So that's another option. You can send me your question, and I'll either write a response back, like type something up, or I'll write something, so you can send me a screenshot of the problem. We can work it out. I just may not be able to hop on to my computer and do a one-on-one session with you on a Thursday or Friday. So keep all that in mind. We're almost done, y'all. We're getting down to the wire. The last 3 chapters. If you need help, please come see me. Well, virtually, Reach out. Let me know. Okay. That's chapter 7. We'll go over it in class. We'll probably do another recap before we start chapter 8 because it's very important that you get it. Until then, stay safe, and I'll see you in class.